Alrighty, good evening, kiddos. It is currently 9:28. Okay, so we're looking at the final review. So this is the physics final review. Now, ideally, if you've watched this, or if you're watching this, you've already spent the time. What, Fiona? Come here. Fiona. Sorry. For the joys of this is listening to my animals. So anyway. Okay, we're gonna pause so I can go put her outside. Okay, and we're back. So ideally, this is to be used as a supplement and not a replacement for your own work. Meaning, what I don't want you doing is sitting there going, oh, I can get all the answers. Because the purpose of this assignment is to help you get ready for the final by understanding how to do the problems. If all you're going to do is look at this and copy down, you're going to get the points, but you're not going to understand it. And in the long run, it's actually going to hurt your grade instead of helping out. So, sorry. Unplugged my computer there for a second. Okay, so let's do this thing. So we start off number 1. An 11 kilogram mass is moving to the right at 8 meters per second. That was my robot vacuum deciding that me making a video was a cue for it to start. Cool. So we're looking for the change, determine the change in momentum of both masses. So the two objects stick together. So if we draw a picture of this, we've got mass 1. It's 11 kilograms. It's going to the right at 8 meters per second. It's been a while since I've drawn on my tablet, so my handwriting sucks more than normal. And to go let my dog in. Be right back. Okay. And we also have a 7 kilogram mass moving this way at 6 meters per second. Now, because we look at the problem, it says they stick together, so we know this is a perfectly inelastic collision, meaning that so this is mass 1, this is velocity 1 initial, this is mass 2, this is velocity 2 initial. We know that because it's a perfectly inelastic collision, the equation we're going to use looks like this. So we have the two masses, their momentum add up, and what is going to be left over is the combined masses of the two and their final velocity. Now, because we know all of these four plus the masses, we can now solve this algebraically for the final velocity. So this is going to be 8 or 11 kilograms times 8 meters per second. This is one of the biggest mistakes you guys made on the test. This is going to be 7 kilograms. Now notice, if this is going to the right, and this right here is going to the right at 8 meters per second, it's going to the left at 6 meters per second, which means its velocity is negative 6 meters per second. Remember that velocity is a vector quantity. Vectors have magnitude and direction. So notice that if I had added those together, instead of going, instead of now I have 88 kilogram meters per second, which is just our units for velocity, minus 42 kilogram meters per second equals, and then we're going to have 11 plus 7 times our final velocity. That's in kilograms. So notice that here, the if we had added those together, instead of ending up with 46 kilogram meters per second, we would end up with 130 kilogram meters per second. So that's a huge swing, simply because of that -6 right there. So now here's the thing. Normally for this, we would then divide by 18 and find out how fast it was going. But here's the thing. We don't need to do that. That's not what the problem is asking. The problem is asking what the change in momentum is. We know that the momentum here, the resulting momentum, this piece right here, the final momentum, is 46 kilogram meters per second. How do we know that? Because the equation is the conservation of momentum equation. Even though we can lose, and we will lose, kinetic energy in a perfectly inelastic collision, we will not lose momentum. So the momentum we start with, 88 minus 42, 46, will be the momentum we end with. And I will quick show you that. If we divide by 18 here, that's going to give me 2 point something. That's going to be my velocity. Now when I take that and if I plug it right back in here, and I go 18 times whatever 46 divided by 18 is, I'm just going to get 46, right? Hopefully that makes sense to you guys. So, for the 11 kilogram object, the change in momentum is our final momentum minus our initial momentum. You're going to notice something kind of funny here. The change in momentum is equal to the momentum of the other object. So because momentum is preserved, when we have a perfectly inelastic collision, the change in momentum of both objects that are colliding is actually the original momentum of the other object. So we had an 88 kilogram object, or an object with 88 kilogram meters per second of momentum hitting an object with negative 42 kilogram meters per second. And when they collide, their change in momentum is equal to the other one. One loses 42, the other one gains 88. Nifty, ain't it? Okay, so that's number one. Number two, Angie has a mass of 85 kilograms. Angie has a mass of 85 kilograms. That is different. So Angie has a mass of 85 kilos. And she is next to a spaceship. Yes, it looks remarkably like a plane. Here, we'll oh, wrong button. Here, we can go like that. That's more space shuttle, isn't it? Then we have, even though it's not moving right now, so let's erase that. So, what's going to happen here? So this is, the spaceship is 800 kilograms. So they're sitting here and they're not moving. So this is mass 1, and the initial velocity is 0. This is mass 2, and its initial velocity is 0. So she's going to give a push to the space shuttle. And that push is going to send her going this way at 1.8 meters per second. Now we're going to call that, because it's going to the left, I'm going to call that negative 1.8 meters per second. Again, it is super important that we understand that momentum is preserved. And in doing so, we need to make sure that we have directional attributes, I guess for lack of a better word, to our velocity. So if one velocity is going right or east or north, let's call that positive. If the other one's going left or west or south or down, we'll call that negative. So, and what we're looking for is, because when she pushes herself off of the spaceship is going to go this way. Angie goes this way, spaceship goes to the right. We want to know what is the velocity of, oh, it's a satellite. It's not even a spaceship. Silly, silly me. So we're going to erase this because apparently on a satellite, it's got like big, it looks like some weird candy. There. That's a satellite, guys. And it has a mass of 800 kilograms. So, again, this is an elastic collision, meaning that we start with two bodies and we end with two bodies. So, our equation is simply the kind of OG conservation of momentum equation. Now, v sub 1I is the initial velocity of object 1. So here we have 85 kilograms times 0 meters per second plus 800 kilograms times 0 meters per second equals 85 kilograms times negative 1.8 meters per second plus 800 kilograms times x meters per second, because we have no clue how fast the satellite's going to go. Here's the thing, though. If she's pushing herself off, she's 85 kilograms, and she's going 1.8 meters per second, we should know that the satellite's going to be going a whole lot slower. So lucky for us, this starts off with a whole bunch of zeros. Okay. And so apparently we're freezing up here, so I might stop this. Let's see. So I'm going to stop this. This will be part 1, and then I'll finish it up in part 2.